one of the most important things in math is to try to extend beyond 3 dimensions. And how do we do that? Well, in this video, we're actually going to explore the interpretations of 4-dimensional objects, and it's by observing the nature of hypercubes, i.e. how we can extend from a 3-dimensional cube, the ones we're familiar with, to a 4-dimensional hypercube that we find difficult imagining. We're actually going to use mathematical equations, patterns, and combinatorics to deduce how many corners, edges, and faces a 4-dimensional hypercube has. Alright, so let's get started. So the first question is to find out the corners of the cube, and we are given that these are the corners. So we get that this is a unit cube, right? I already denoted a length of 1 over here. And think about it. If we have this corner over here, then the corresponding coordinate is 0, 1, 1. If we have this point, then the corresponding coordinate is 1, 1, 0. If we have this very diagonal corner over here, then it has the coordinate 1, 1, 1. Alright, so we can basically deduce that a corner coordinate has components 0s and 1s. So let's list out the permutations of 0s and 1s we can have in a 3-component coordinate. We have 0, 0, 0, and I'm going to list out the rest. You can try this yourself first. Looking at this, we have 8 possible combinations, which is consistent with the 4 given corners plus the other 4 corners. This is a really interesting property, because that provides us an insight into counting corners in 4 dimensions. We now know that the number of corners of a cube is the number of permutations a 3-component coordinate with 0s and 1s have. We can treat the coordinate as a list, or a tuple, if you will. And let's look at how this works. For a 3-component coordinate, we have 3 components, right? Each of these 3 components could take on 2 possibilities, 0 or 1. Notice that the order of components does matter, because we have 1, 0, 0 that is different from 0, 1, 0. Although they only have the same number of 0s and 1s. Henceforth, the total number of possibilities we have is 2 to the power of 3, which is 8 possible corners. That is to say, a way to interpret the number of corners in a cube is to interpret how many possible permutations we can have with only 2 possible values for each component, 0 or 1. Well, this exponential, which is 3, is indicative of the dimension we're working within. We're going to use this relation between the dimension and the exponent to derive a general formula for an n-dimensional cube. Next of all, we want to find the coordinates of the center point of the cube. Well, that's pretty easy. The center point of the cube is the average point for the x, y, and z coordinates. This means that the coordinate for the center point is simply a half, and half. I'm going to write this out. Naturally, we have to assume that this cube has a uniform density, but that doesn't really matter in this video because we are not going to be focusing on weighted averages and other more exotic stuff. Now, what is the third question? We want to find the center points of these 6 phases. This is very similar to finding the center point for the cube. Well, the center point is over here, and over here on this top surface. And we have to recognize is that these phases have something in common. If we have this phase, let's consider this phase. Well, this phase has what I called a parallel phase. The parallel phase is over here. which is a distance of 1 from this face. If we have the bottom face, this bottom face is a distance of 1 from the top face, which is its parallel face. And so the only thing we have to do is to find out what the coordinates are for the center of the three faces, and then we can add a distance of 1 to find the other faces. Alright, so how do we do that? Well, let's first find out what is the center point on this face. Well, the center point is on this face. We go a half unit to the x direction and a half unit to the z direction. So this is a half, 0, and a half, because we don't get anywhere in the y direction. This means that if we add 1 in the y direction, then we get the center point for this face, its parallel face, which is a half, 1, a half. Now notice what is the difference. The x and z coordinates stay the same, they stay as 1 half, but the y coordinate changes from 0 to 1, and this will be very important. For this bottom face, the center point is namely, let's see, we go again 1 half to the x, but now 1 half to the y direction, and so this is 1 half, 0. Going 1 unit up in the z direction, we get a half, and 1. Notice that the only thing changing is the one component that is not 1 half. That component changes from 0 to 1. It's kind of like a binary property, that for each component we have two possibilities, or we have a fixed possibility, which is 1 half or 0 and 1. Fair enough. Thus, the number of faces in our cube is essentially equivalent to how many center points there are. This is because we have two components that are 1 half, and we have one component that is not a half, which can either be 0 or 1. So literally, we can list out the combinations there are. We don't have to resort to the image anymore. These are the permutations that give the center points for each faces by arranging the two a halves and the zeros and ones. Alright, and that's really interesting because now we have 6 faces, which is correspondent to the number of center point coordinates. That will be very useful when we're trying to figure out the number of corners in a cube with 4 dimensions. Alright, let's extend to 4 dimensions. For 4 dimensions, we're not going to use the picture anymore. How can we figure out the number of corners in a combinatorial sense? Well, it's the number of permutations we can have with 4 components in 4D. Of course, where each component has 2 possibilities, which is 0 and 1. This implies that for a 4-dimensional hypercube, we have 2 to the 4, which is equal to 16 possible corners, because there are 16 ways to arrange the coordinate only containing zeros and ones. Alright, let's get rid of that. Now, how many 3D faces does our hypercube has? That might sound a bit weird because you might ask, how can we have a 3D face? Well, if you think about it, for a 3-dimensional cube, what we're considering is a 2D face, which is like a plane. However, for a 4-dimensional cube, what we're actually interested in is a structure composed of 3D faces. Alright, so let's consider the number of faces we can have. Well, notice what we talked about over here. We can find out the number of center points for the faces. For a 2-dimensional cube face, we can have 2 components of 1 halves. So for a 3-dimensional face, we have 3 components of 1 half. For example, this is one possibility. This is another possibility. You can get what I mean by 3 components. Fair enough. It's literally another problem of combinatorics. Now we can find out how many ways we can arrange these 1/2 in this 4 elements list. This is analogous to saying, for example, how many ways we can choose 3 people from a 4-person group. Well, it's using combinations. 4 choose 3. This is equal to 4 factorial over 1 factorial and 3 factorial, which is equal to 4 factorial over 3 factorial, which is 4. But notice, now that we have arranged a halves to each of its possibilities, we need to also multiply this by 2. 4 times 2 is 8, because we have a binary possibility for the remaining component that is not 1/2, which can either be 0 or 1. So the value 4 is how many ways we can arrange the 1/2, but we also have to multiply it by 2 to count for the remaining possibility that we are left with. Hence, we have 8 faces over here. To be more precise, I should say 8 3D faces. And now, let's talk about edges. How many edges are there? Well, the number of edges there are. We haven't talked about that in our 3D case, but we can actually use a similar strategy to how we've figured out the number of faces, using the midpoint of each edges, namely the center point of each edge. Now notice that for each of these midpoints, they only have one component that is a half. All other components are zeros and ones. So it's literally kind of analogous to what we did over here in the faces, but we limited our number of 1/2 to only one component. So a possible permutation is a half, 0, 0, 0. Right, another possible permutation is a half, 0, 1, 0. These are all different permutations we can have to figure out the number of midpoints for the edges. Well, this means that to find the number of edges, it amounts to showing how many possible permutations of midpoints we can have when we only have 1/2. And all the remaining coordinates can have either a value of 0 or 1. Now, to find this number of permutations, it's basically the number of possible places we can put 1/2, which is 4, multiplied by the number of possible values these things can take on, which is 2 times 2 times 2. This is 4 times 8, which is 32. Well, you might be confused. Why are we multiplying 4 by these numbers? But if you list them out, let's say, you have a half, and if you treat this as a subset of 3 components, this 1/2 is going to stay fixed there. What we have is a sub-permutation. Well, there's 2 times 2 times 2 combinations over here, right? But the 1/2 can also be the second component, so we have another 2 times 2 times 2 over here. It can also be the third component, so you can have another 2 times 2 times 2. It can also be the fourth component, and ditto. Therefore, for this particular problem, we have 32 edges for a 4D hypercube. I'm just going to write out the general formula for the number of phases and the number of edges and the number of corners, since right now I think you already get what is happening. You can basically apply the formula of combinatorics to figure out the number of edges, corners, and faces you have. For the number of corners in n dimensions, I'm just going to write nd. The number of corners in nd is 2 to the n. It's literally because for each component, we have 2 possibilities. And in n dimensions, there's n components in each coordinate. So we basically multiply 2 times 2 times 2 n times. So ultimately, we gain 2 to the n. Now, the number of edges in nd. The number of edges in nd is, let's see, the number of places we can put a halves multiplied by the remaining sub-permutation. We can have an nd with n components n places to put 1/2. So we have n times, we have n minus 1 remaining components, and each of these components have two possibilities, two possible values they can take up. So we can have 2 times 2 times 2, n minus 1 times. Which means that this is equal to n times 2 to the n minus 1. That is the general formula. What about the number of faces? For faces, it's a bit different because we can have 2-dimensional phase, a 3-dimensional phase, a 4-dimensional phase. So let's talk about n minus 1 dimensional faces in ND. Well, if you think about what we did, when we were talking about faces, we used permutations. And what we did is we multiplied this permutation by 2. Because ultimately we're going to be ending with one remaining component, which can take up two values. So for n minus 1d faces in ND, we can have 2 times this combination. Well, this combination is basically n choose n minus 1, but n choose n minus 1 is always n, so this is 2n. This is the number of n minus 1d faces and n dimensions, 2n. Which is pretty beautiful, right? And notice how these are really consistent with our 3D measures. In 3D, we have 2 to the 3, which is 8, and there are 8 corners. For edges, we have 3 times 2 to the 3 minus 1, which is 3 times 2 to the 2, which is 12 edges. Yep, there's 12 edges in a cube. And for 2-dimensional faces, in a 3D cube, we have 2 times 3, which is 6 faces. And it's the same for a 4D hypercube. And that's all from me. These are the ways you can figure out the number of corners, edges, and faces in an n-dimensional hypercube.